Hey there. Let's talk about something we all use every single day, but probably don't think twice about: the battery. Seriously, these little things are the tiny engines that power our modern, untethered lives. So I think it's about time we figured out how they actually work.
We've all been there, right? You're in the middle of something important, and then that final, sad little beep from your phone as the screen goes dark. It's the worst. But why does that happen? And how do these little metal tubes hold so much energy in the first place? Well, that's exactly what we're going to dive into.
So here's our game plan. We're going to start with the basics, in the world of electrons. Then we'll look at the anatomy of a battery, get into the chemical reaction that makes it all happen, figure out why they all eventually die, and finally, see how we can get more power and a longer life out of them.
All right, first up, let's shrink down and enter the world of electrons. See, before we can understand what's happening inside a battery, we kind of need to know what it's trying to do in the first place.
So what even is electricity when you boil it all down? It's really just the flow of these unbelievably tiny particles called electrons. The battery's entire job, its whole purpose in life, is to create a push that gets these electrons moving through a circuit, like the one in your TV remote.
And believe it or not all electricity is created equal. Batteries give us what's called direct current, or DC. Just think of it like a river. The electrons are all flowing smoothly in one direction. But the power you get from a wall outlet? That's alternating current, or AC. In that case, the electrons are flowing forwards and backwards, kind of like the tide of the ocean.
And what gives those electrons that push? Well, that's something called voltage. The absolute easiest way to think about voltage is to picture it as water pressure, right? The more pressure you have in a pipe, the more powerfully the water shoots out. It's the same idea here. The higher the voltage, the more pressure is pushing those electrons through the circuit.
Okay, with the basics covered, let's get to the main event: the anatomy of a battery. We're going to digitally peel back the layers of a regular old AA battery and see what's really going on in there. So inside that boring steel case is this amazing little chemical sandwich. On the positive side, you've got the cathode. This is kind of the electron's final destination. It's a mix of manganese oxide and graphite. Then, on the negative side, you have the anode, which is the electron source, and it's made from zinc powder. Now, what's super important is that they're kept apart by a separator so they don't touch, and the whole thing is soaked in the electrolyte, a solution that's basically the highway that lets the whole reaction happen.
Now, for the microscopic engine that drives this whole thing, the chemical reaction, this is where the magic happens. And here's a key thing to remember. A battery doesn't actually store electricity. No, it stores chemical energy, and it converts it into electrical energy whenever you need it.
And the story of how we discovered this is just fantastic. It starts back in the 1780s with a scientist named Luigi Galvani and a frog's leg. Yeah, he noticed that if he touched the frog's leg with two different metals, it would twitch. He thought he'd discovered animal electricity. But another scientist, Alessandro Volta, he wasn't so sure. He argued it was the metals causing the twitch, not the frog. And to prove it, in 1800, he built the world's very first battery, just a stack of zinc and copper discs with some salty paper in between.
And that was the huge aha moment. Volta's incredible insight that you could create a flow of electricity just by putting two different materials together with a chemical solution. That is the foundation for every single battery we use today, from the one that starts your car to the tiny one in your watch. So how does this electron dance actually work in our battery? Well, it all starts at the negative end, the anode. A reaction happens where the zinc atoms basically give away their electrons. Now, all these free electrons start to build up, and they are desperate to get to the positive side, but that separator is blocking them. The second you turn on your flashlight, though, you create a highway. The electrons rush out, power your device, and then re-enter the battery at the positive cathode, where another reaction basically welcomes them home. And that constant flow, that stream of electrons racing from the negative side to the positive side, that's it. That is the electric current. As long as that chemical reaction can keep going, the electrons keep flowing, and you've got power. Which, of course, brings us back to that awful moment when your phone dies. So section 4, why do all batteries die? I mean, if this chemical reaction is so great, why can't it just go on forever? Well, it really depends on the battery. For a normal single-use one, it's pretty simple. It runs out of gas. The zinc at the anode gets completely used up and there's nothing left to give away electrons. For rechargeable batteries, that reaction is actually reversible. When you plug it in, you're just pushing the electrons back to where they started. But it's not a perfect process. Think of it like folding a piece of paper over and over.
Each time you add tiny little creases, and eventually it just gets worn out and can't go back to being perfectly flat. The battery slowly loses its ability to hold a good charge.
All right, last section. Let's talk about how we get batteries to do exactly what we need them to. This is all about how we combine them and measure their energy to get more power or more life.
Now, this is a really important idea. How you connect batteries totally changes what they do. If you connect them in series, positive to negative, like in a big flashlight, their voltage adds up. So two 1.5-volt batteries give you 3 volts for a much brighter light. But if you connect them in parallel, positive to positive and negative to negative, the voltage doesn't change, but their capacity, their lifespan, doubles. So you don't get more power, but it lasts a whole lot longer.
And that brings us to capacity. You've probably seen mAh on a battery package. It stands for milliamp hours. The best way to think of this is like the size of the battery's fuel tank. A battery with 2500 mAh can, in theory, provide a certain amount of power for a specific amount of time. The bottom line is, the higher the mAh number, the longer that battery can potentially last.
So there you have it, from a twitching frog's leg all the way to the tiny engines that power our entire world. But this story is far from over. I mean, scientists are working on the next generation right now, batteries that are lighter, safer, and can be recharged tens of thousands of times. So the real question isn't just how batteries work today, but as our whole world comes to rely on them, what will the battery of the future make possible?